P-H-Y, papa, P-H-Y, P-H-Y, papa, P-H-Y. Physics. Welcome!
Welcome to another AP Physics Camp lecture. Today we're going to be reviewing uniformly accelerated motion. No, Alex, I said uniformly accelerated motion, not that you need to wear a uniform. Uniformly accelerated motion means that you are accelerating at the same rate. Yes, that's right, Alex. Uniformly accelerated motion is basically referring to an object in motion with constant acceleration. Okay, let's get started and make sure that you take good notes. Okay, so let's take a look at an example in which an object is constantly accelerating. Yes, Alex, good example. If we were to look at a toy car in an inclined track and we ignored the friction, we could say that the acceleration experienced on this toy car would be due to gravity, relevant to the angle that it is inclined in. Yes, Alex, we would expect the acceleration experienced on this toy car to be greater at a steeper incline, in other words, at a higher angle, especially one closer to 90 degrees. Why do you think? That's correct, Alex. 90-degree incline is basically saying that the object is simply being dropped. And in physics, we refer to this as a free-falling object. Now, this would be our next lecture, where we're going to focus our attention on vertical motion, in which acceleration is due to gravity and can be expressed as 9.8 meters per second squared, or simply rounded to 10 meters per second squared. Now, as for today's lecture, we're simply going to focus on what constant acceleration looks like, both graphically and mathematically. Let's first start graphically, using our example of a toy car on an inclined racetrack. Okay, Alex, before we get started, tell me what data you would need to collect in order to determine the toy race car's acceleration. Yes, that's right, Alex. So in order to do that, we're going to use several photogates to record the time that it takes for the toy race car to move through the track. No, Alex, that's not what the term photogate means. A photogate is a piece of physics equipment which emits a light beam. The photogate is connected to a timer, which records the time that it would take for an object to break the light beam. I know that it might sound a little overwhelming, so instead, let's try looking at a photogate to understand how it works. Here's the setup photogate. Notice the beam that is emitted across the device. Now, if the car was released and it passed through the device, then the moment that the car breaks the light beam on the photogate, the timer starts. And the moment that the car no longer is obstructing the beam, in other words, when the car has finished passing through the device, the timer stops. Good question, Alex. In order to determine the velocity, we would need to know how much the car traveled during this time. So think about it. The time that was recorded was based on how much time it took for the light beam to be broken. So what would be the distance here? Yes, Alex, that's right. The distance that the car traveled during that time frame would have been basically the length of the car, since the light beam was broken the moment the tip of the car passed the light beam and started the timer. And then the moment the end of the car passed the light beam, in other words, cleared the obstruction, that ended the timer. Thus, the distance or displacement that that car traveled between that time frame was its own length. Now, what do we do with this information? We can now calculate the car's velocity at this point in the track, which would be, you got it, Alex, the velocity at this point on the track would be calculated using the length of the car and dividing it by the time recorded on the timer. Good question, Alex. Remember that we're working with vectors and that negative is a way to identify direction. Since the car is traveling downward, we will identify it as the negative direction. That way, if the car were to go back up the ramp, it would be in a positive direction. So what about acceleration? Can we calculate that? Yes, that's right, Alex. We need another velocity since acceleration is final velocity minus initial velocity divided by a change in time. So then what do you think we can do to get another velocity? That's right, Alex. We can use another photogate and determine the car's velocity at another position in the track, while also recording how much time it took the car to travel from the first photogate to the second one, giving us our change in time. Okay, let's try it out. Now you need to make sure that both photogates are clear from obstruction before releasing the car. All right, ready, set, go. All right, Alex, let's take a look at our timer and see what it tells us. Notice how the time for the first photogate is displayed when I check on the photogate input button. Then when I click on the second photogate input button, the second time is displayed. Okay, so we already know the velocity for the first photogate. So now let's calculate the velocity of the car at the second photogate. You got it, Alex. To get the velocity of the second position on the track, you need to divide the length of the car divided by the time recorded for the second photo gate. All right, so now we have the two velocities of the car at two different locations on the ramp. Now we can calculate the change in velocity, which is final velocity minus initial velocity. Yes, that's right, Alex. The velocity calculated from the second photo gate was our final velocity. The velocity from the first photo gate is our initial velocity. And when we subtract the two, it gives us our change in velocity. But what about the change in time? Yes, that's right, Alex. If we were to select both of the photo gates on the timer, we would be given the time recorded for the car to travel between the first photo gate and the second photo gate, which is our change in time. You got it, Alex. We can divide our change in velocity by this change in time, and it will give us the acceleration of the car between this time frame as it moves down the inclined track. But would the car experience the same acceleration throughout the entire ramp? In other words, is the acceleration constant? Remember, we are ignoring friction. You're right, Alex. To answer this, we need to determine the velocity of the car at different locations on the ramp, not just these two, and then determine the acceleration between each of these. For instance, we can determine the velocities at these other locations as well by moving the photo gates across the ramp. So let's label these locations as the following: A through E. Now, let's say that the photo gate at point A will be our starting point, in other words, time 0, which means that the second photo gate will be the one that will continue to move down the ramp to determine points B through E. So let's now move the second photo gate to point C to collect the data, and then move it again to point D, and then again to point E. Okay, now that we have all of our data collected and we have calculated the velocity of the car at points A through E, as well as the time frames in which the car traveled through these photo gates, what motion graphs do you think we could create? That's right, Alex. Based on the data that we collected, we could develop a position versus time graph in which we would use the position of the photo gate on the y-axis and the time frame between photo gate A and another on the x-axis. This would result in the following trend. So, Alex, what do you think this trend illustrates? Yes, that's right. The slope of a position versus time graph is velocity. And since we see it curve, it tells us that the slope is changing. Thus, the velocity is changing, which means that we do have an acceleration. But what graph could we use to help us determine if the acceleration is constant? That's right, Alex. We could use a velocity versus time graph in which the velocities at point A through E would be used on the y-axis and the time frame between photo gate A and another would be used on the x-axis, resulting in the following trend. So, Alex, what do you think this trend illustrates? That's right, Alex. Because the velocity versus time graph slope illustrates acceleration, we know that since the slope is the same on the straight diagonal line, then the acceleration is constant as well. Now, if we were to calculate the acceleration between each point, we could also develop an acceleration versus time graph. What do you think the line would look like here? That's correct, Alex. Since the acceleration stayed the same, meaning constant, or better yet, the car was uniformly accelerating, then the acceleration versus time graph would display a horizontal line at the acceleration value, which was negative 467, or negative 4.67 meters per second squared in this case. Yes, Alex, that's right. If we were to increase the angle, as we mentioned before, the acceleration would increase, causing the car to move faster. Eventually, if it were inclined close enough to a 90-degree angle, we would see that the acceleration would be close to negative 9.8 meters per second squared, which is the same acceleration that is recorded when an object is in free fall. Keep in mind that both would be experiencing constant acceleration when friction is ignored, which is why we refer to these examples as uniformly accelerated motion. Now that we know how to use motion graphs to illustrate the motion of an object that is uniformly accelerating, we're now going to focus on how to use a mathematical approach when graphing is not the most efficient method to use based on the information provided. For instance, we have identified a total of 5 different variables related to motion. Can you list them? Yes, that's right, Alex. The 5 consist of initial velocity, final velocity, change in position, acceleration, and time. But sometimes we don't know all of the variables, thus graphing would become very difficult, which is where the mathematical approach comes in by using the following major kinematic equations to solve for a missing variable. Yes, Alex, you heard right, kinematics. This term is used to describe a branch of physics that studies the motion of objects. In other words, kinematics consists of those 5 variables that we listed listed. And if you notice, these kinematic equations consist of them as well. Now, what else do you notice about these equations? Yes, Alex, that's right. These kinematic equations are basically derived from both velocity and acceleration formulas, which means that we can use them to solve for missing variables when acceleration is constant. In other words, these kinematic equations only apply when an object is uniformly accelerating, but the key is knowing which equation to use based on the information given. Let's try out an example. Take a look at this horizontal racetrack. Notice how there is no incline here. Now the race car is going to start at rest in the 0-meter mark on this frictionless racetrack, and it's going to race for a total of 0.4 seconds at a constant acceleration of 6 meters per second squared. What was its final velocity and final position? Okay, Alex, what do you think we should do first? That's right, Alex, we should first list out our 5 variables. That way we can identify what we know and what we're looking for. So let's see. We know that the car was at rest, therefore it had an initial velocity of 0. And we are asked to find the final velocity, so we're going to place a question mark here. Now, as for the change in position, we don't know this, but we do know the initial position, which is important because a change in position is the final position minus initial. And this particular problem is asking for final position. Thus, we could have a question mark on the final position minus the 0-meter mark, which is our initial position. Now, we know the acceleration is 6 meters per second squared, and the total time was 0.4 seconds. So now that we have listed it out, now what? Good idea, Alex. We could color code what we know and what we don't know so that it's easier to identify which kinematic equation to use. For instance, let's highlight all of the known variables green on all the kinematic equations, and then yellow the variables that we don't know on the kinematic equations as well. Remember that in order to solve for a variable in these equations, we must only have one missing variable in the equation. So based on that, which equation could we use first? That's right, Alex. We could solve for the final velocity using the first equation, or we could solve for final position using the third equation. Okay, so let's try it out. Good job, Alex. The final velocity would then be 2.4 meters per second. Now, what about the final position? Yes, that's right, Alex. The final position would then be 0.48 meters. Notice how we use these kinematic equations to solve missing variables of an object that was uniformly accelerating in a horizontal motion. But we can also use these for vertical motion, which is what we're going to use in our next video lecture when we discuss objects in free fall. We refer to these types of motion problems as motion in one dimension, meaning that it's either in the horizontal or vertical motion. So what do you think two-dimensional motion problems would look like? Yes, that's right, Alex. Two-dimensional motion problems would consist of vectors and components such as seen in inclined planes or projectile motion, which we're going to discuss in greater detail in later lectures. Yes, Alex, you're right. Two-dimensional motion would allow us to take into account the angle of the incline and the acceleration due to gravity to determine the acceleration of the race car experienced on the track in our very first problem. This concludes our video lecture. Make sure that you took good notes, and that's it. Have a great one.